Cancer is, unfortunately, governed by the same evolutionary rules that drive life itself. Cells in tumors are essentially competing to see which can divide the fastest. This competition drives them to pick up new mutations that can help them divide faster, survive immune attack, resist drugs, and expand to new areas of the body. We can tell this by looking at the genetic changes that occur as tumors progress. Over time, we can trace the appearance of new mutations that confer abilities that are, from cancer's perspective, useful for tumor cells. Now, a new study suggests that an unfortunate side effect of these evolutionary changes is that human tumors are really difficult to study. Whether the tumor cells are put in a culture dish or grown in mice, they evolve changes that help them grow in this new environment. And some of these changes influence how the tumor cells respond to drugs. Options, all of them bad. It's possible to study cancer immediately after the removal of cells from a patient. But that only works for a limited amount of time. Instead, scientists have typically induced the cells to grow in a dish, surviving on a steady flow of nutrients delivered using a liquid medium. Some cancer cell lines have been maintained for decades using this approach. Unfortunately, the approach is also limited. To begin with, a culture dish can't capture the complex interactions that cancer cells have with the normal cells around them or the immune system and metabolism of their hosts. In addition, some research has indicated that cells kept in culture pick up mutations that help them survive in a dish. To get around these issues, some researchers have started growing human cancer cells in mice. While this isn't the same as growing in a human, the mice are immunocompromised. To keep their immune system from killing the foreign cells, it's thought that this would provide an environment that better reflects what the cells would experience in a human body. To an extent, that's probably true. But some researchers decided to see whether the mouse was an equivalent environment to the human body when it comes to the evolutionary pressures that the cancer cells face. To do so, they focused on large changes in the genomes of the cancer cells, big duplications or deletions of DNA that encompass multiple genes. By altering the dose of several genes, these copy number changes alter the gene's activity with potential consequences for the cell's health. Copy number changes are also relatively easy to detect. The team used everything from genome sequencing to gene activity assays to determine when cells had gained or lost clusters of neighboring genes. Tracking changes to make comparisons, the researchers obtained samples from 3 different sources. One was a collection of tumors and metastases taken directly from a patient. A second was a set of tumor cells that had been grown in a culture dish. And, finally, they obtained tumor cells that had been grown in mice, in some cases transplanted to new mice as the original ones grew sick and had to be euthanized. The most obvious result is that the cells underwent genetic changes in all of these environments. In some cases, the changes were similar, but in many others, there were changes that were distinct to each of the environments. In other words, some genetic changes aided tumor cell survival in humans but not in culture dishes or mice, and vice versa. These changes took place quickly. Over half of the tumor cell lines ended up with a large genetic change after spending time in one mouse. Nearly 90% of those that had been moved to another mouse 4 times picked up large changes. On average, these changes affected over 10% of the genome. Strikingly, humans and mice caused selection of very different changes. For some tumors, growth and metastasis in humans favored the loss of specific genes, with their deletion present in the majority of tumor cells. In fact, as far as the researchers could tell, these genes had been completely lost from all cells. But apparently, they were still present in a small subpopulation, because the presence of the genes was favored in mice. After several transfers through mice, the majority of tumor cells had the genes in question. In other cases, genes where extra copies were selected for being in humans vanished when grown in mice. All in all, opposite genetic changes in humans and mice, gain versus loss of a gene or vice versa, were more common than cells experiencing similar changes in both organisms. The big problem, however, is that some of these changes alter how the tumor cells respond to drugs. In other words, a drug that seems ineffective when tested in mice might actually work in the human patient in which the cells originated. Or a drug that works in mice might prove to be useless in the patient. The fact that cancer cells will adapt to their environment isn't a surprise. The fact that a human and a mouse provide such strongly different environments, however, wasn't entirely expected. After all, people were using mice precisely because they were thought to provide a more realistic environment to study the tumor. This doesn't mean that mice studies are useless, it just indicates they have to be treated with appropriate caution. And, since many researchers will continue to use this approach, it will provide us an opportunity to better understand the consequences of the genetic changes that occur when human cells are grown in mice. With a better grip on this biology, we might be able to make some inferences about which types of studies are likely to remain directly relevant to human health. Nature Genetics, 2017. doi 10.1038 nanograms.3967 About DWA. This post originated on Ars Technica.